thank you. Thanks so much for inviting me. It's really great to be here. So, well, I was sort of trying to think about this thing about how to define inertial frames, and there's a non-trivial chance that I'm just reinventing the wheel by thinking about this perennial question. So that's one caveat. The other caveat is sort of I'm unashamedly interested in this talk in coordinate-based formulations of Newtonian mechanics, right? So maybe half of the people in the room will say, why bother with inertial frames or inertial coordinates? We've got this nice sort of differential geometry framework, and isn't that sort of the absolute truth about it? But I think that sort of, historically and philosophically, of course, all these coordinate-based formulations have been very important, and it's maybe worthwhile to just try and understand, what's going on there and how do we really define the things that we're talking about. And in particular, the question that I'm most interested in is, right, many people do think that the inertial frames or the inertial coordinates provide some sort of privileged way to represent certain structures, spatiotemporal structures in a theory like Newtonian mechanics. And I want to sort of understand that relation between the structure itself and the representation of that structure and where that comes from. So we'll start with something that I'm sure everyone knows, Newton's laws. So I'm not going to read them out, but I don't think we usually use the laws like they're written like that. Probably if you open a high school textbook on physics, you get something like this. It's going to say, these sort of expressions using coordinate-based mathematical objects, right? So we've got the velocity of all force-free bodies is 0, so we've got the derivative of some velocity vector, we've got something to do with forces, right? But this is the crucial thing, those equations don't just hold true, sort of whenever. It's a bit like if I say, the house is on the left, that's just an incomplete sentence. I have to say on the left of what is it, right? It's on the left of my house, but you can't just sort of generally say it's on the left, right? So the bit with these equations, if I say f equals ma, that's sort of empty of content if I haven't specified, what coordinate system I'm using. It might be true using one coordinate system, but false using, say, an accelerating coordinate system, right? So when we write down the laws like this, we're going to have to preface them and say, these things are going to be true in any inertial system of coordinates, right? If we use the inertial coordinate system, then these things are going to be true, right? So if we sort of take that to be our high school physics theory, then in order to apply that theory, we need to know what are those inertial systems of coordinates, right? If we don't have those, then we can't even sort of check whether the laws are true or use them to make predictions. So it does seem to be a sort of a crucial starting point for this whole enterprise, as long as we're doing things in this coordinate-based way. So that's really just a question, how to define the inertial frames. And I'm going to discuss various approaches that I've sort of found in the literature that I'm unhappy with, and then discuss my own approach that doesn't seem to be as prominent, although there are some precursors, but that I think is sort of the best, the best for reason that we'll see way of doing it. So I'll start with discussing something called the law-based definition. So this defines the inertial frames in terms of at least one or more of those laws in the coordinate-based formulation that I've just written down on the slide. I think this is sort of the thing that most textbooks tell you the inertial frames are, and that most sort of people, when you ask them, quick, define an inertial frame, this is what they'll say, so we'll come to that. But it does seem to be a sort of very unsophisticated definition that I think is open to a devastating objection. In particular, it's too weak, so it defines too many frames as inertial. So that will lead to the laws being true even when we don't want them to be true, as it were. So the second definition, I call them structure-based definitions. They're based on the structure of spacetime. So they say we don't just talk about the laws in order to define the inertial frames. We also need to look at spacetime itself and what sort of spatiotemporal structures we think the theory has. So I think this is something we found a lot in philosophical discussions, but again, I wouldn't call it quite too weak in this case, but too flexible. The sort of idea of how coordinates relate to space-time structure is too flexible to do the work that we require it to do to offer a good definition of inertial frames. So Brian mentioned I did some work on symmetries, so it won't be surprising that I will advocate something I call the symmetry-based definition. So I want to say, when we look at the dynamics, the equations of motion of Newtonian mechanics, they have certain symmetries, right? Typically certain coordinate transformations that leave the form of the laws the same. Those symmetries will give us an important reason for privileging certain coordinate systems over others. And those will turn out to be just the classical inertial coordinates that we desire. So I think it's really the symmetries of the dynamical equations that sort of pick out the inertial coordinates as a privileged class of coordinates with respect to which to evaluate those laws. Good, so that's just the plan to go through these definitions, and we'll start with the law-based ones. So, don't know if anyone ever used a Merton textbook when they studied physics, but he's got this nice limerick which basically expresses exactly what I take the law-based view to be, which it says, for things moving free or at rest, observe what the first law does best, defines a key frame inertial by name, where the second law then is expressed. Right, so the idea is, take the first law, which says that force-free bodies travel at constant velocity. Now construct coordinates such that within those coordinates, the velocity of exactly the force-free bodies, which I'll assume for simplicity that we can sort of non-controversially identify, which obviously is controversial, but suppose we have some good criterion, right? They're very far away from everything else, and maybe there are no actual force-free bodies, but we can sort of say, what would a force-free body do if it were moving somewhere? Suppose all those problems are solved, and we've got the force-free bodies. We look at the coordinate systems in which the derivative of the velocity of those bodies is 0. Those are the inertial frames, and then having found those inertial frames, we can look at, is the second law true and the third law, right? Do they hold true within those frames? And if so, then the laws of Newtonian mechanics are satisfied. So here's sort of my less poetical phrasing of this definition. It says, an inertial coordinate system is a coordinate system in which force-free bodies move with constant velocity, right? So in which dv by dt is 0. I suppose I should quickly just say something about this term coordinate system and inertial frame. So I take a frame is going to be something like an identification of, say we've got a space-time manifold that's basically going to tell us what counts as the same location over time. So sort of, say, picking a few bodies and saying their sort of lines of motion are going to be our constant locations. But in the end, the notion that is more interesting from my perspective is the idea of a coordinate system, which is basically going to be a function from space-time points into forcibles of real numbers. Or if you don't want to commit to anything like space-time points, it could also be a function, from sort of parametrized particle trajectories into triples of real numbers. But it's going to be some sort of assignment of real numbers to locations, whether those be space-time points or the locations of particles. And there's some sort of relation between the frames and the coordinates, but I think what we need in the end is a coordinate system, right? Because that's what we need to evaluate expressions like dv by dt. We need to assign coordinates to particles, and then we can do things like differentiate those coordinates with respect to parameter time. Okay, so this is the inertial coordinate system. Here is my objection. I sort of called it the triviality objection because I think in a way it tells us that this definition is trivial in a sense that we can sort of almost always satisfy it. So consider these two worlds, right? One is a world in which there are n free particles and they all move with constant velocity. Right? So this is sort of a world that we should intuitively think of as Newtonian, right? There are force-free bodies, they're very far away from each other, and they all move with constant velocity. Brilliant. And I suppose there's another world, W star, which is exactly like W, except that one of the particles, right, is not moving at a uniform velocity. It's sort of, doing a sort of strange, swervy motion, haphazardly moving about. I think Merton has this phrase that it's doing a fancy jig. It's not doing what we wanted to do if we were living in a Newtonian world, right? So W star, sort of by stipulation, is a world in which Newtonian mechanics is false. But the aim of the objection is to show that if we hold on to this law-based definition of inertial frames, we can in fact construct an inertial frame which counts as inertial in W star and in which Newton's second and third law are satisfied, which means that it will turn out to be a law in which the laws of Newtonian mechanics in their coordinate-based formulation hold true, sort of contradictory to the assumption. So there's one slightly non-trivial assumption, which is that there will exist a diffeomorphism from W to W star, which maps the trajectories from each particle to trajectories of the same particle. So basically what that means is that, you know, these sort of worlds at least agree on whether particles sort of intersect and whether they form sort of knots in their trajectories, right? But that's going to be the case sort of almost always. So yeah, that's just a small sort of caveat. Yes?
So you say that the particles move out capacity. Are you taking motion as being absolute, or are you saying they move relative to some? Is the motion relative to some fixed thing, or is it absolute motion, or what?
Right. Well, suppose at least we can sort of take the distances between them to be given, right? And we can use that to sort of say that at least one of them is sort of increasing and decreasing in distance with respect to all the others. So I think that's the sort of the minimal thing we need. We need there to be a fixed notion of distance. Right? We don't need anything like absolute space. Okay, so now, suppose we define an inertial coordinate system for W, right? Call it X. So X mu is just my notation for coordinate systems, so these functions from spacetime into spacetime coordinates, and define a coordinate system for W star, which basically, well, I want to be slightly careful with sort of saying the same space-time points, given that we're talking about these different worlds, but speaking loosely, you know, for each particle, it assigns the same coordinates to the particle in W star as it would have had in W, right? So essentially, you know, take any given particle at any given time, suppose there is sort of a unique way to map times between W and W star, then at each time, each particle will have the same coordinates according to X prime in W star as it has to X in W. Okay, good. I hope that's clear. The fact that all the particles will have the exact same coordinate values in each world in their respective coordinate systems, of course, means that according to X prime, all the particles in W star are at rest, right? And because we've supposed that all the particles are force-free, this means that Newton's first law is satisfied in W star with respect to our constructed coordinate system X prime, which means that X prime, by the law-based definition of an inertial frame, is an inertial frame or inertial coordinate system. Okay, well that's no reason to worry yet, right? Because it might be an inertial coordinate system in which Newton's laws are false. But that's not the case, right? Because Newton's second law, for example, says that force is proportional to acceleration. These bodies are force-free, so the force in each of them is zero, and they're also moving at constant velocity, so their accelerations are also zero. So it will turn out that Newton's second law is also satisfied, and of course Newton's third law is satisfied as well. Right? So by our definition of inertial coordinates and our phrasing of Newton's laws as saying that, you know, these things hold with respect to the inertial coordinates, it's going to turn out that W star is a physically possible world according to classical mechanics. Well, absurd is maybe a little too strong, right? But I feel like this should give one pause, right? And so, for example, as I mentioned in response to your question, you know, these worlds differ in the distances between bodies, right? So one couldn't sort of just say, well, I'm a relationist and I believe that everything is the same up to distances, because even the distances here are different. So the relationist would still have to say that these are different worlds, and it would sort of seem, even to a relationist, that W star is not a Newtonian world, right? I can imagine someone who's got a strong operationist bent, who basically says, you know, things like distances and forces are defined in terms of our inertial coordinates, right? So how do we even know whether these bodies, what the forces and distance of these bodies are? Well, we have this sort of operational procedure to construct inertial frames, right? Which is something like try to get as many of these bodies to move with constant velocity, and then these worlds turn out to be the same. I I mean, yes, I just don't have, an operation is leaning, so for me that's not really an option, but that could be one sort of point here to get off the boat and say, I'm happy with this, I sort of have this strong operation is leaning. Yeah, Brian.
Sorry if this is for discussion, just tell me, wait for discussion. I think it's clarificatory, but when you say that it's distances that distinguish the two cases, I'm not so clear on that. I thought I was following, but then that made me think I wasn't. So I'm just imagining, it's very much like the whole argument what you're describing, of course. It's like I'm just imagining two inertial trajectories, and now I imagine two bent trajectories after applying phi. And, that phi, if I'm going to, I guess the question is, aren't I also applying phi to the metric, in order to say that, if you're telling me that the velocity is zero and the acceleration is zero, it's like with respect to the original fixed metric, if I now give you this bent curve, it's an accelerating curve with respect to that metric. So what I think one rather means is that we apply phi to the metric as well. I've got G star, and with respect to G star, then yes, of course, this is an inertial trajectory, and I follow you completely. But then I wouldn't just say that the distances are all the same, because, I've messed up the trajectories, but I've also now stretched the distances as well. And in the whole argument literature, some, the relationists would say, you are describing exactly the same situation as you were before. The relational facts remain the same, so W and W star are one in the same world.
Yeah, good. So I didn't intend to apply phi to the metric, right? So let me just draw something to make it clear. I know I'm not as good a drawer as you are, but right, suppose we've got something like our sort of space-time grids, right? And this so each box would sort of be an equal distance, and then we've sort of got ticks of time. Right? And so in W we've got some sort of straight traveling particles, and then in W prime we've got sort of one particle just doing this sort of fancy jig, right? And now I'm thinking the distances, right? They're clearly different. So like here, for example, right, we see that the red line here will have different distances from these lines than the blue line. But we could assign different coordinates to these, right? So we could sort of say, these are just sort of going to be numbers we assign to each point. And the numbers I assign to each point could be different in each case.
But when you say that then I would understand what you're saying is what justifies saying that these are different numbers, that these are different distances, is the underlying coordinate system. So in the original underlying coordinate system, I would say the two original inertial trajectories, their relative distances are different than in the new system, where I've got now what looks like a straight line and what looks like a wiggly line in your drawing.
Yeah.
So I mean, or maybe there's just the freedom to make this choice, and I've just gotten mixed up. Sorry. So the way you drew it just now.
I'm thinking if we've got something, like dv by dt, that's evaluated not with respect to sort of the grids, it's with respect to the numbers we assign to the grids.
Yes.
Right. But I'm saying keep the grid fixed. I can assign any numbers I want. Until now, you might sort of say, I mean, this preempts the next slide. You might say, you can't really assign any number you want to the points in the grid, because they have to sort of respect, the structure of the grid. So equal distances in the grids have to be given equal numerical distances. Right? But that's the next step in the dialectic. So yeah, now I'm just saying, keeping the grid fixed, we can assign any numbers, but if we have that freedom, then it's too easy to construct a system in which the derivative of v by t is going to be 0.
Good. Yeah. I see. Thanks.
Right. Do you want to?
I think it's possibly related, but again, let me know if this is coming later on for the discussion. But I've understood it in different Moore systems tend to include accelerating a frame. So in special relativity or Galilean relativity, you have a fixed symmetry group, and that implements inertial transformations. But once you add diffeomorphisms, you can accelerate the reference frame, and that's why you need some sort of covariance theory. I don't know if I've got the right end of the stick, but can you rule out what's going on here is simply your transformation implicitly includes adding a force which accelerates into by changing the frame to one which involves acceleration?
Yeah, well, I mean, I guess the thing is you can do more than just accelerate, right? You can accelerate, but you can also rotate, or sort of time-dependent rotation. I don't know why the accelerations would sort of play a special role there.
But what I mean is, if you've got the diffeomorphism, that seems to be to implicitly add in a force, because by moving from W to W to W star, you've made a symmetry transformation in the diffeomorphisms, and that, it seems to me, involves the rotation or acceleration. And if that's the case, there must be a force that corresponds to the acceleration or the rotation.
Right, well, look, I think, and it's all very good, but you're all thinking in a very coordinate-independent way, right? Which is obviously the right way of thinking, but I wanted to think about this very coordinate-based way, right? So in the coordinates-based way, write down some force law, right? We could write down F equals m over r squared, gmm over r squared, right? But again, these particles are very far away, so the force is just going to be 0, right? So, we can change the coordinates any way we like. We're not changing what sort of forces are acting on the body because they remain very far away from each other. But, there's a sort of a thought there which says there should be sort of a force that's making this particle do its strange trajectory, right? But, well, here's a quote by the great Harvey Brown, which might express some of the intuitions that everyone's having. Harvey says, the coordinates x mu are special not just because the equations of motion expressed in terms of them take a special simple form, right? They're also special because the coordinates, they should also be special in relation to the metrical properties of space. Right? When Newton talks of uniform speeds, he means equal distances being traversed in equal times, and these distances are meant in the sense of Euclid. Right? So I think Harvey to be saying something like, I can't just assign any arbitrary numbers to the points in this grid. Right? If I've got 2 points on the grid that are equally far apart, I have to assign them coordinates that are equally far apart by some sort of standard of what it means for coordinates, how far apart they are, right? So this is what I call a structure-based definition. It's saying inertial frames should also in some sense respect the structure of space. And so on such definitions, an inertial coordinate system would be defined as a coordinate system that is adapted to the metrical properties of space and in which free bodies move with constant velocity. So there's one sort of small point here, which is that you might suggest why the metrical properties of space, why not the affine properties of space, and then we can do away with this condition about force-free bodies, right, which is sort of define everything directly in terms of an affine connection, as it were. What it turns out, this is shown in this paper by Ullmann and Friedman on inertial coordinates, these things would be equivalent. So the coordinate systems adapted to some postulated affine structure just are the coordinate systems adopted to certain metrical properties in which force-free bodies also move with constant velocity. So I've chosen sort of to focus on this requirement of metrical properties, one, because I find it conceptually simpler, but also because you might think it's sort of more neutral between relationism and absolutism. Right? Even a relationist agrees that there is some sort of metrical structure, not of space, but sort of metrical spatiotemporal structure, whereas the relationist might not always be happy to countenance affine structure. So that's why the focus on metrical properties of space here. And so this idea, right, that we could have coordinate systems adapted to the structure of space is very popular in the philosophical literature. So Eamon says every spacetime will have a preferred set of frames that reflect the structure inherent in the spacetime. Tim Maudlin says the intrinsic geometrical structure of space and time, according to Newton, entails that special sets of coordinates exist. The existence of such convenient coordinates follows from the spacetime structure itself. Whereas Oliver Pooley says both substantivalists and relationists will view certain coordinate systems as kinematically privileged in the sense of being optimally adapted to the particular spatiotemporal quantities that they each recognize. Right? So in each of these quotes, there is this idea that there is a certain spacetime structure, and somehow certain coordinate systems sort of best fit that spacetime structure. But it's often less clear what exactly this means, right? Which coordinates then are best adapted to this spacetime structure. And so one has to dig a bit deeper to find out what people think. Nick Huggett, for example, says, and he says, in Euclidean space, a frame is adapted to some reference body if it is at rest at the origin of the frame, the axes are orthogonal, and distances along the axes equal the distances from the body. Right? But I find this still somewhat puzzling. We're talking distances from the body. Okay, suppose those are given by your Euclidean metric, that's some space-time structure. But what are the distances along the axes, right? If the axes are sort of just idealized rulers with engravings in them, right, sort of numbered engravings, then what are the distances? What is the distance between 5 and 10, for example, right? And so Oliver Pooley makes this a little bit more precise. He says, the ways in which a coordinate system can be adapted to these quantities is straightforward. Okay? Spatial coordinates are chosen so that for all particles I and j, and for all times, right, this expression, xi minus xj, equals the distance, where the distance is the instantaneous interparticle distance between I and j. Right? So Rij there is the distance given by, say, the Euclidean metric. Xi and xj are coordinate expressions of the particles I and j. Right? So if we've got a coordinate system x mu, then that will give us xi and xj given those particles. Right? And then this function is basically the Pythagorean metric. So I think I've got it on the next slide. Well, let me just write it down. Right? So that's just sort of going to be this, familiar expression. So it's a particular function of triples of coordinates, right? It's some sort of function, right? And we could sort of ask, where does it come from, right? Why that function? So let's make this a bit more precise, technically speaking. When we think about a metric function, right? A metric function has nothing to do with coordinates. A metric function on a space would just be a function from pairs of points of that space into the real numbers. Right? And it would satisfy certain axioms, right? It'd be symmetric, for example. If it's a Euclidean metric, it would satisfy additional axioms. Don't need to go into those, right? But the idea is, given any 2 points in space, it would give us a real number which represents the distance between those points in some particular units, right? So in the sense that the real number might just be 5, and we've sort of said, well, that's going to be 5 meters, and if it be centimeters, then we'd have a different function, right? So suppose we're working with particular units. Well, that's a metric function, but it doesn't tell us anything about, how to use coordinates to express those distances. And for that, we need something which we could call a coordinate representation of a metric function, which will be a function from pairs of coordinates of particles into the real numbers, such that whenever we've got 2 particles and we assign them coordinates, then this function of pairs of coordinates will give us the same number as the metric would give us, right? So this is the idea. Suppose, we've just got the distance between I and j, then this function, the Pythagorean metric, is a coordinate representation of the Euclidean metric if and only if this expression here will just equal the distance between I and j as given by the Euclidean metric. Now, obviously, that's only going to be the case in certain coordinate systems, right? So one could sort of do this one of 2 ways. Either we could start with certain coordinate systems and say, what are the functions that will just give us, given 2 particles, what will be the function from their coordinates in that system, such that we get the distance they have given by the Euclidean metric, right? Or we could go the other way and we could say, given a function r, right, from the coordinates of particles into the real numbers, what are the coordinate systems, what are the ways of assigning coordinates to particles, such that that function in that coordinate system will just give us the distances between those particles themselves, right? And so, for example, when we've got the Pythagorean coordinate representation of the Euclidean metric, it's just going to turn out that the coordinate systems in which that function represents the Euclidean metric are the familiar Cartesian coordinates, right? So that would exclude my sort of gerrymandered coordinates that I used in my criticism of the law-based approach, because those coordinates, given those coordinates, if we applied the Pythagorean coordinate representation, we wouldn't get back the distances given by the Euclidean metric, right? So what this shows is that fixing on a particular coordinate representation of the metric, we can indeed narrow down the class of coordinate systems to certain ones that we indeed might want to think of as inertial, right? For example, the Cartesian ones. So yeah, so here we've got the Pythagorean coordinate representation, right? So it seems to me that what Huggett and Pooley really claim is that a coordinate system x mu is adapted to the Euclidean metric if and only if it's the Pythagorean distance, as it were, between those particles' coordinates will always equal their real physical distance as given by the Euclidean metric. But why the Pythagorean coordinate representation, right? Why not any other coordinate representation of D? And you know, obviously there exists infinitely many. We can sort of play the same trick using diffeomorphisms, and I can, you know, sort of pull back any coordinate transformation to define a new function, which in the new coordinate system will give the same distances as the Pythagorean metric gave in the old coordinate system, right? So it seems to me that at least the people in this debate, right, this is sort of their stopping point. They say, oh, obviously it's the Pythagorean coordinate representation, right? And I sort of want to keep going and say, well, but why that one? And so, right, the reason is that if we're not fixed on the Pythagorean metric, we can again get some sort of triviality objection going, right? So consider these same two worlds, right, with the same diffeomorphism, and define this new sort of new coordinate system in the same way, right? So x prime now is not adapted to the metric if we take a Pythagorean coordinate representation, but we could define a new coordinate representation, which is just defined such that its value for any two particles within the coordinate system x prime is the same as the value of the Pythagorean representation of the metric for any two particles in the original coordinate system, right? And now by definition, x prime, by definition, this new function r prime represents the Euclidean metric within the x prime coordinate system, right? So I say x prime is also adapted to the Euclidean metric, right? But it's adapted to the Euclidean metric only if we use a different coordinate representation of that metric, right? We're using r prime rather than the Pythagorean function. But at least up until this point, it seems that we can just make this choice, right? We can say, I'm going to represent distances given by the Euclidean metric by some function. Well, I've chosen r prime. Having chosen r prime, my gerrymandered coordinates are going to be adapted to the Euclidean metric, right? But obviously this spells trouble because, again, Newton's second law, right, is also going to be satisfied in W star with respect to x prime. That's just what we saw in the previous case. Therefore, again, we get this conclusion that, you know, there is some sort of adapted coordinate system in which the laws of Newtonian mechanics are satisfied in W prime, contrary to the stipulation or the intuition that W prime is not a Newtonian world, right? So what we need then is some sort of way to privilege the Pythagorean coordinate representation over any other way of representing the Euclidean metric. And so I think there are a few responses one might give here that I'm not quite happy with. So the first one would just be to arbitrarily stipulate that, right? So I could just sort of rephrase my Newtonian mechanics. You know, recall that at the start I had the slide that it said for any inertial coordinate system, you know, I could sort of say for any inertial coordinate system in brackets, the one that's adapted to the Pythagorean coordinate representation of the Euclidean metric. You know, that could just be my formulation of Newtonian mechanics in a coordinate-based way. And I mean, you know, this is just going to be a point where people are going to differ in their approaches. So for some people, that's a perfectly happy stopping point. I sort of want to say, well, but couldn't we give any sort of explanation for why it's the Pythagorean representation of the Euclidean metric that will give us, you know, these nice and simple laws which will hold in a classical universe. Right? And maybe that's just the way it is, but I believe that I can actually give an answer for why it's the Pythagorean representation, right? Which sort of means that, therefore, I'm unhappy with just stipulating it. A second response, and Tim Mortlin seems to have this response, although he also had this quote earlier where he said that it follows from the spacetime itself that we have these Cartesian coordinates. He also just seems to say that the Pythagorean metric is the most convenient or simple or easy to work with, right? And that's what privileges it. So I think the first issue with this is just sort of general issues with the notion of simplicity and its role in physics. right? So how do we define simplicity? Why would we not think that simplicity is just sort of thoroughly subjective, right? And that maybe to us, this function, the Pythagorean coordinate representation is very simple, but maybe for some alien community of scientists, that would actually be a very non-convenient representation, and they'd find some other function very convenient. Right? We could also say, even if we think that there is some sort of sense in which the laws, the way I've written down the laws of Newtonian mechanics are simple, that might not be the same notion of simplicity as the simplicity of a representation of space-time structure, right? Is it really the same idea of simplicity that reoccurs in both of those questions? So I mean, these are sort of very general reasons, but then also, right, suppose it is true that the Pythagorean metric representation is the most convenient or the simplest, right? Then suppose it's also true that the sort of these, F equals ma is the simplest coordinate-based formulation of Newtonian mechanics, right? There are no sort of fictitious forces and such. Then we get the sort of double coincidence. Why should the laws in their simplest form happen to hold true exactly in the simplest coordinate representations? Right? Again, this is something where presumably some people will say, well, that's just the way it is, aren't we lucky? But I sort of, one, find that puzzling and would like to give an answer to that, give an explanation. And two, I think I've actually found an explanation, so I sort of feel that given that there is an explanation, any approach which just takes it as primitive, they're clearly missing out on something. And then finally, Jill North seems to have this idea that certain representations are just sort of inherently more direct or more natural or more perspicuous in virtue of the space-time structure itself, right? So just take Euclidean space, for example, some coordinates will just inherently more naturally or more directly reflect the structure of Euclidean space. And so one question I have is just how does one define what it means for a representation to be most natural, most perspicuous, most direct? I find that, although Jill North does a great job on this and says many interesting things, I feel that she doesn't really define what she means by these sort of notions. And also there might be a slight sort of circularity here. Right, so here's an example of what I mean. Take any sort of map of the Earth, right? I mean, as I'm sure we all know, none of these maps is perfect, right? Because we're projecting a sphere onto a square piece of paper, so there are going to be some distortions, right? So for example, in the Mercator projection, the further north we go, or the further away from the equator, the sort of landmass area seems to be much larger than it is in actuality, right? And this is why sort of on the map, Antarctica and sort of Northern Europe are much bigger than they are relative to Africa, for example, compared to their real sort of areas, right? So you might think that North has something like this in mind. She says, look at the Mercator projection. Clearly, that's sort of a less direct or less perspicuous representation of sort of the globe of the Earth rather than if we just had a 3D globe. And my point is basically that that's only true if we've already implicitly adopted a certain representational convention, right? So the convention we're adopting is that in order to find out the landmass of a continent from the map, we just sort of take the actual area on the map of that continent, and then we say, well, that's going to be proportional to its landmass in actuality. Right? Well, that's one convention, but one could have a different convention which says, in order to find out the landmass of a continent on Earth, we take the map and we do this sort of weighted procedure whereby, we weigh the bits of the map further to the north or further to the south, less than we would do the ones right down in the middle, right? And obviously, if we do that, we could set up an alternative function by which we could indeed calculate the proportions between land masses of continents using the map. It's just that we need some sort of alternative rule to go from the map to the actual Earth, right? But it's only with respect to the first rule, right, which might indeed be more intuitive or more natural, that we think that the Mercator projection is somehow deficient. If we set up another, admittedly non-sort of standard way of representing certain facts about the Earth, then in fact it turns out that the Mercator projection or any other kind of map encodes the exact same information as a globe would, right? So it's only once we've already adopted the representational convention that we can say that certain representations are deficient. but that doesn't really help us in choosing which representational convention to adopt. So that's why I don't want to take the naturalist route. Okay, so these are ways that people have tried to defend something like using a Pythagorean representation. Now I'm going to the final part where I'll say how I've justified using that sort of nice function. And so I think Landau and Lifshitz sort of say something in the vicinity of what I'm trying to say, which is that the inertial frames are the frames in which space is homogeneous and isotropic. But it's sort of unclear what they mean by that, so I'm trying to make that a little bit more precise. And I want to say something like this: a coordinate system that represents the metrical properties of space in a symmetry invariant way, and in which force-free bodies move with constant velocity. So what do I mean by saying that the metrical properties of space are represented in a symmetry invariant way? Well, start with the laws as I've written down, F equals ma and so on, right? They're invariant under certain coordinate transformations, right? These ones. And so the fact that the laws are invariant under these coordinate transformations, that when we apply these transformations, they retain the same form and the same satisfaction conditions, that gives us some reason to believe that it doesn't really matter which ones of these coordinate systems we use. Right? Take any given coordinate system, apply a Galileo transformation, I get a new coordinate system. The fact that these are dynamical symmetries gives us reason to say it doesn't really matter which of these coordinate systems I use. But it's going to turn out that if we just take an arbitrary representation of the metrical structure of space, then given one of those functions that will calculate the distance given the coordinates, those functions will not always be invariant under Galilean transformations. So what that means is I could have a certain arbitrary coordinate system and an arbitrary representation function that just works out such that, given that function, the distances between particles given by their coordinates work out to their actual distances as given by the Euclidean metric. But if I then apply a Galilean transformation to those coordinates, keeping my representation function fixed, it's going to turn out that suddenly the particles have very different distances between them. That seems to be the kind of situation that we don't want based on the dynamical symmetries of Newton's laws, right? Newton's laws and their dynamical symmetries basically tell us when we represent the distances using some function on coordinates, we'd want that function to be invariant under the Galilean coordinate transformations because those are distinctions without a difference, to use a Leibnizian phrase. So what that gives us is basically a few constraints on this representation function R. Right? So one is it says, given the coordinates of any two particles, if we add a constant vector to their coordinates, we want that function to remain the same. We want them to give the same distances. Right? So that's translation invariance. Likewise, we need rotation invariance. Well, that already tells us that this representation function R has to be a function of, of this quantity. It has to be a function of the Pythagorean metric representation. Right? It's not yet identical, and in fact, it could be a very trivial function. Right? It could assign 1 to any non-identical particles and 0 to any identical particles. So we're not there yet. So the third condition we need is something called absolute homogeneity. And this deserves a little comment, because scaling transformations are not symmetries of the laws of Newtonian mechanics, right? But this is something like a scaling transformation. We're saying apply a scalar multiplication to all the coordinates, and then we need to also, the distance then needs to be scaled by the same amount. So basically the way I want to justify this condition is by thinking about these as passive transformations rather than active ones. Right? So while it's true that actively thinking, it's not actually a symmetry to just increase the distances between everything. Passively speaking, right, if we sort of multiply all the numbers, if we change all our meters to centimeters, right, so we multiply all the numbers in our grid by 100, right, that's a symmetry. We think that the laws of Newtonian mechanics are units, they're unit independent. And that's how it should be. It shouldn't be that they're true if we use meters, but false if we use centimeters. Right? And that explains why this is not why we have the multiplicative constant there, because we're saying when we multiply all the coordinates by a positive constant, we also want the distances themselves to be multiplied by that same constant, because in effect what we're doing is we're just doing a coordinate transformation, a unit transformation. We're going to say from meters to centimeters. And once we've got that condition, it follows that our coordinate representation must be the Pythagorean representation up to some constant alpha, which just tells us which unit we've selected, right? So we can vary alpha to go from meters to centimeters. So what we now have done is we've derived the Pythagorean representation from certain dynamical conditions, right? So we don't need to appeal to any pragmatic considerations. We don't need to appeal to some inherent facts about space-time structure. In particular, in my view, it could be the case that space-time structure is the same, but the dynamics are different, and that would in fact lead to a different class of privileged representations of that very same space-time structure. Right? But we seem to have some non-arbitrary reasons for choosing this Pythagorean representation, which will in the end give us the Cartesian coordinates, right? By saying that given that function, our coordinate system has to be adapted to the metric.
Can I just clarify how I understand what the statement of the theorem? So the context is one in which you're dealing with Riemannian metrics only, I assume, because obviously those three are satisfied by the Poincare group as well.
Yeah.
And in that context, homogeneity and isotropy, so rotational invariance and translation invariance, are known to be true of only three metrics that are the Euclidean constant positive curvature and constant negative curvature. And then the latter two don't satisfy dilation symmetry.
Right.
And therefore, because if you scale a sphere, you're getting a different geometry. And so you're stuck with the Euclidean geometry. So it's this sort of theorem that you're describing right now, is that?
Yeah, I hadn't thought about it in that way. Partially because I'm thinking about I'm not thinking about the metric tensor, right? I'm thinking about the metric function.
It's the same,
but
in this context, it's the same fact.
Yeah, so I think, that sounds right.
But one has to be careful here in the generality of your statement, of course. It's like Pythagorean only follows when we already assume we have a Riemannian signature. Because if I were to treat xi and xj as in these statements as having, and your R function as having a Lorentzian signature, I would find all the same facts hold of Minkowski spacetime if you think about it. It also has this character.
Yeah, right. So I mean, given that I was working in the context of Euclidean space, I might have sneaked in some assumptions that, basically the metric function we have satisfies something like the triangle inequality and so on. But that's a good point, and I should definitely be sure to be clear on that. So drawing to the end, here's a quote again from Harvey Brown. I forgot to put the page number on there. Right, he talks about the influential 1973 article by Ehrman and Friedman, right, and they claim, according to Harvey at least, that no rigorous formulation of the law is possible except in the language of four-dimensional differential geometry. But the appearance of systematic studies of the four-dimensional geometry of Newtonian spacetime is relatively recent, right? So it's curious that so much success has been achieved by astronomers applying Newton's theory of universal gravity to solar systems well before that date, right, using this coordinate-based way. How could this be if they were unable to fully articulate the first laws of motion and hence the meaning of inertial frames? Right? How tempting it is in physics to think that precise abstract definitions are, if not the whole story, then at least a royal road to enlightenment. And so, on the one hand, I think Harvey Brown makes a good point in that, we shouldn't just throw away all this sort of history about coordinate-based formulations just because we've now found, the holy grail of four-dimensional differential geometry. On the other hand, I'm more sanguine than Brown about, precise abstract definitions. I think, hopefully, that what I've done has put the idea of inertial frames on a more precise and a surer footing, where we can actually, use the mathematical structure of the theory to arrive at a good definition of inertial frames. So here are the sort of conclusions I want to draw. So one is this idea that it is possible to offer a precise abstract definition of inertial frames. Importantly, this definition does not follow from the space-time structure itself, right? If someone gave me Euclidean space without any dynamics, I could not conclude using my reasoning that we should only use Cartesian coordinates, or that those would somehow be the best ones. Right? We really need to go through the dynamics, look at the dynamical symmetries to construct the right representation function, which will only then give us the right class of coordinates. And finally, right, this sort of emphasizes the crucial role that symmetries play in physics. It doesn't seem from the literature that many people think that the notion of an inertial frame is sort of connected to symmetries in this way. Obviously, there are connections in the sense that have to be invariant in the Galilean transformations, but on my view, their sort of definition relies on these symmetries. So that's a broader lesson. Good, so I hope everyone enjoyed that. Hopefully I haven't entirely reinvented the wheel. Thanks for listening.